Now we will talk about the little different student t distribution. So what is the t? So actually this is the t value. As you can see, that this is t value. This is similar to the z value. The actually role of the t value is the same as the z value, but you can think the t value is kind of modified z value. So that's why we use a t instead of the z value. When should we use is when the standard deviation is unknown. When standard deviation is unknown, what we have to do is we have to use a sample standard deviation, right? So when we know the standard deviation, we can do this way. However, when we don't know the population standard deviation, that's in really this most case, we are not sure about this S, right? In this case, when we know the standard deviation, I know the standard deviation, so actually I can tell this is the value. However, when we have to use S, the sample standard deviation, you are not sure about this part. Then can we just use Z, or should we enlarge our interval a little bit? So I want to have a little bigger number than Z. So here this is the t. So that's why the t value is greater than the z value. So I want to use a t which is slightly bigger than z. Actually, some cases are a lot bigger. Depends on the sample size. Sometimes it's slightly bigger, but anyway, it's bigger than z to enlarge the interval. Why I want to enlarge? Because I'm not sure about this number. I'm pretty sure here the calculation is the standard deviation divided by square root of n. But when I use a sample standard deviation, because I don't know, I'm not sure about this standard deviation. So I want to have a little more safe, conservative way. So to make sure it's 90% or 95% confidence level, so you have to enlarge this range a little bit. So how much more bigger? That depends on the n. So we will talk about it later. So student t distribution is similar to the normal distribution, but it's slightly different. And then student t distribution depends on the n. We will use a degree of freedom. Actually, degree of freedom is n minus 1. So n is a sample size. So basically, student t distribution will be similar to the normal distribution, but it will be a little different. Now t value is greater than z value, and how much greater will depends on this degree of freedom, which is the n minus 1. So as n is getting bigger and bigger, as you can see here, t distribution is getting close to the z as n increase. So as n increase, n increase, t is going to the z value. So here the degree of freedom is the n minus 1. This is for mu, or the mean. So for the different statistics, degree of freedom can be different number, but in our course, you will see only degree of freedom is n minus 1. So for our class, you can consider all the degree of freedom is n minus 1, but actually that's not true. Outside of this class, degree of freedom can be n minus 2, n minus 3, but however, in this course, we will see only the degree of freedom is n minus 1. So you can just use a degree of freedom as n minus 1 here. Comparison of the z and the t. For very small sample, t value is a lot different from the normal, so t is a lot bigger than the z. But when n is getting bigger and bigger, the t will be very similar. So 90% confidence interval, we would use t is 1.967, but z is 1.645. So t is greater, but with the 30, it's not a lot greater, it's a little bit more greater. But if you have a more and more sample, higher the degree of freedom, then your t is getting close to the z value. Let's take a look at the the example, GMAT score. So if you have a GMAT score, so this one, so you collect the 20 applicant, so you don't know what is the population mean, and you don't know what is the population standard deviation. So this is the 20 different value, and you calculate the sample statistics here. This is the sample statistics. Right? So mean is 510. So this is what we estimate is the mu would be 510. Actually, I know x bar will be exactly same as mu, but that's the if this is the only one, so we can estimate mu using x bar. And s is the here. But however, how can I find the mu can be greater than x bar and smaller than x bar? But how can I create the 90% confidence interval? So if we keep doing this confidence interval, 90% of the case will contains 90% of the confidence interval will contains the real population mean. So we can create it here, but since we don't know what is the sigma is unknown. That's why we cannot use a z value, so we will use a slightly bigger one. But since n is 20, you can find out the value. So you take a look at the table. This table will be the t value table. So confidence interval level, you can find it at 90%. So 90% will be the upper tail area. So I'm keep explaining this again and again. If you want to have a 90% here, then this part will be the 0.05 because this part will be 0.05 too. So that's why it's a 0.05. And then you can look up the degree of freedom is 19, so you can find the t value. This is the t value, which is greater than z. So once you find the t value, then you can calculate the confidence interval. Plug into the here number is 510 is x bar, and the t is 1.729. And s is a sample standard deviation, and n is 20. So you can plus and minus, you can find out this one. So it will be interval will be 481 and 538. So our real true mean, the population mean, will in between 481 and 538. With 90% confidence. So here the 90% confidence does not mean 95% probability. It's a little different story, right? So I explained that. So don't confuse by the statement. So if you want a narrow interval with the same level of confidence, so we have to larger our sample size. So this will be the width of the interval. This is the center, right? This part is the plus t s over square root of n. This is minus t s over square root of n. So actually this width is 2 times t s over square root of n. So this is not the number you are trying to find out, and then t is the also you are not deciding. So n you can change, right? So if you want to narrow, so you have to better have a large n, then you can have a narrow interval. But if you have a smaller n, then you will have a wider interval. Confidence interval width will be affected by the sample size of n. As I told you, the t, s over n, or z sigma over n. But this is not my choice. This is not my choice. So only thing is you can change is the n. Or you can choose the confidence level. So only thing you can change is alpha or n. But sigma, s or sigma is not your choice. We don't have a control over the standard deviation. So you can change these two things. If you want to have a tighter, narrow confidence interval, then you can lower the confidence level or increase the sample size. Student t distribution assume the normal population. So population is normal. While this assumption is sometimes is in doubt, but actually many cases student t's are reliable as long as population is not badly skewed and if the sample size is not too small. So the student t can be a problem only when population is badly skewed and also sample size is too small. So when sample size is large enough or the population is not badly skewed, then student t will be fine. So whenever the sigma is unknown, then you better use a t value rather than using the z. So there isn't much justification of using z when sigma is unknown. So whenever the sigma is unknown, you better use t value instead of z. Confidence interval for the population, not population, it's a proportion. Confidence interval for a proportion. So actually the proportion is the counting yes or no. So how many yeses we have out of n trial, all right? So that's about the proportion. Proportion occurs frequently in the survey. So we find the p is x over n, and out of n sample x number of success we can find, and this is the estimate of the pi of population proportion. But can we calculate the confidence interval for the proportion again? But same as we know the z sigma over square root of n, we're gonna plus minus this one. But here in the proportion we can find the standard deviation. What is the proportion standard deviation? Is the p 1 minus p, right? Or real thing is the pi is 1 minus pi. So you can just simply replace this one into here, then you can get a confidence interval. Okay, so the sample, this is a sample proportion. So this is the actually the pi is 1 minus pi, and then divide by square root of n. Then you can just simply merge square root of sign. Right? That's how you got this form. And then if you replace the standard deviation, actually you can get a confidence interval of proportion. So simply this one is a 0, 1 distribution, and then you will have a proportion. But when the n is large enough, we can tell this is the, as you can see, this is 5, 10, 20, and 50. As you increase the number, this will follow the normal distribution. So normal distribution assumption is still fine. However, this can be very skewed. If your success rate, the P, can be really large, really small, or P is really large, then it can be very skewed. When this is really small, this can be happen, right? And then if the probability of success is too big, then this can happen. Then this is a lot skewed, then you will need a lot of sample size to justify the normality. So how can I find out it's not badly skewed or not? So you will check the two sides. This is greater than 10 and this is greater than 10. So either way, right? If it's very small, but small, still the number is greater. So n times the pi is greater than 10, then we can say, okay, this is not that badly skewed. Or the other side, n times 1 minus pi is greater than 10, then you can say, yeah, this is not badly skewed, so we can assume the normality. So that's the two room. That's why we are checking both sides. I don't know which side is skewed, so you can just check the tail part. And then if it's greater than the 10, then we can say this is not that badly skewed. Okay, so table shows a very large sample may need a normality. So assuming normality, when the pi's differ greatly from the 50. So if your sample is too small, so this is a kind of the required sample size. So if the pi is really small or really big, then which means it's skewed, so we need a lot of the sample size. But if it's not skewed, it's symmetric, I don't need a lot of the sample size to justify the normality. Confidence interval for the pi will be something like this. But actually this is the same as the p plus minus z sigma over square root of n, because the sigma is replaced by the p 1 minus p, right? That's it. If you just replace it, then you will get exactly the same formula here. So it looks like a totally different formula, but actually you just replace from the previous confidence interval, sigma is the p times 1 minus p. Then you will get exactly same confidence interval formula. So you use the same z for the same confidence interval, right? Let's take a look on an example. The sample of the 75 retail in-store purchase show the 24 was paid in cash. So you can calculate the P is 24 over 75, which is a 0.32, you can see here. That's my sample proportion. So we will construct a 95% confidence interval for the proportion of all retail in-store purchase that are paid in cash. So now I want to know the pi. So of course the pi, the best estimation here is a 0.32, but I want to create the confidence interval, 95% confidence interval. And you can say pi will fall in between these two numbers, will be in this range with a 95% confidence. So you can just check the normality, right? So NP is 24 and n times 1 minus p is 51. So both of them are greater than 10. So we can say this is not badly skewed. and then you can just plug in the number, then you can create the confidence interval. Here is the plus minus 0.106, and then you can say, I don't know what is the population proportion. That population proportion will fall in between 0.214 and 0.426 with 95% confidence. Okay. Yeah, we cannot know the certainty whether true proportion lie within the interval, right? But we can say on average 95% of interval constructed in this way, again, that's the same way. If we created an interval this way, same way, only difference is the different sample, and 95% of that interval will contain the true population proportion. That's what we express is 95% confidence. If you want to reduce margin of error, but again, the margin of error is this is we call the margin of error, or the T S over N, or Z P1 minus P N, right? So this is the margin of errors. So how plus minus from the mean. So width of the confidence is affected by the confidence level, right? And then standard deviation, and here this is this case. So it's affected by P, alpha, and N. Again, this is we don't have a control over, so we can change the sample size or the confidence level. So if you increase the confidence level, this will becomes widen, and if you increase the sample size, this will be the become narrow, right? It's a different way. If you increase the sample size, you become more confident, so you can narrow. But if you increase confidence levels, which means you have to make sure the population proportion will fall in between here, so you have to enlarge. I mean, if you have to widen the interval, so you have to understand what happened when you increase the sample size, what happened to the interval, and if you increase confidence level, then what happened to your interval.